Hello and welcome to FlippedHarrber for Precalculus. In this video we're going to cover section 1.1, topics from algebra and geometry. Now since this is our first video for FlippedHarrber for Precalculus, I wanted to remind you that you should really be taking notes. Those notes are going to go in your binder, and I could draw on them as questions for those binder quizzes. So it's really in your best interest. Get some paper, get a pencil, and start taking good notes. Our objectives for this lesson are to learn how to express a range of numbers using interval notation or inequalities. We also want to look at how to simplify and evaluate expressions containing both absolute values and exponents. We also want to look at using the Pythagorean Theorem to find the length of a missing side of a right triangle, as well as using the Pythagorean Theorem to determine if a triangle has a 90-degree angle. Our topics for this lesson include interval notation, absolute value, exponents, polynomials, and the Pythagorean Theorem. The outline for this video is we'll start with the interval and inequality notations, then we'll move on to absolute value expressions, we'll look at some exponents rules, and then we'll take a look at roots, we'll take a look at using exponents and roots on numbers, we'll look at exponents on variable expressions, and finally end with the Pythagorean Theorem and take a look at the section's homework. So let's get started. Here we see a range of numbers from -4 to 3. The closed dot at -4 means that we need to include the number 4, but the open circle at 3 means we don't want to include 3. So we're going to look at how to express this range of numbers using both interval notation and inequality notation. Now interval notation looks kind of like an ordered pair, x comma y, but it's really a beginning value and an ending value. Now you'll notice that there's a bracket around the -4, but a parenthesis around the 3. The bracket means that we're going to include that number. The parenthesis says don't include the actual number 3. Now one thing about brackets and parentheses, when you're using either positive or negative infinity in interval notation, you want to remember to never ever put a bracket on infinity. You can only put parentheses on infinity. Looking over at inequality notation, we have -4 is less than or equal to x is less than 3. So again, it's all the numbers from -4 to 3, but -4 is included. Positive 3 is not included. Let's take a look at some absolute value expressions. And really what's important is for you to remember that anything inside an absolute value bracket, you need to think of it as being inside parentheses. It's one of the first things that we do in the order of operations. So we have two very similar absolute value expressions, the absolute value of x plus y and the absolute value of x plus the absolute value of y. Now we're going to plug in some numbers for x and y and take a look at the different answers that we're going to get under these two similar but very different circumstances. We'll plug in -5 for x and 6 for y. In the first expression, we need to add the two numbers before we take the absolute value. In the second expression, we need to take the absolute values and then add. In the first case, we get an absolute value of 1, which equals 1. In the second expression, we're left with just 5 plus 6 because the absolute value of -5 is 5 and the absolute value of 6 is 6. So in that case, our answer is 11. So again, you need to remember what gets done first. The absolute value brackets act similar to parentheses in the order of operations. So anything inside the absolute value needs to get done first. Let's take a look at some exponent rules. Now you should be familiar with all of these, but let's review them. If we're multiplying two things with the same base, like a to the m times a to the n, because they're both powers on a, we'll just combine them by adding the exponents. If we have a power to a power, we can combine those powers by multiplying. Now if we have a product that's raised to a power, if we want to, we can distribute that power. Now we can only do this under certain cases, and we absolutely can't do it if it's a plus b. Only if it's a times b, or we'll see another time that we can do this in a second. Whenever we have a negative exponent, I like to think of it as that negative is telling me that the term is in the wrong part of the fraction. So a to the -m, that negative is saying that the a is in the wrong part of the fraction. it's in the top, it belongs in the bottom. As soon as I move it down to the bottom, it becomes a positive exponent. Now similarly, if we have a negative exponent in the bottom of a fraction, if we move it to the top, it becomes a positive exponent. Now if we have a power on a fraction, we can also distribute the power to the top and bottom of the fraction. So instead of a over b all raised to a power, we can distribute that power to the top and bottom separately. And the last thing you need to remember is that whenever you see a zero power, that term is equal to 1. All of these rules are true whether we are using variables or numbers. So you need to remember a variable to a zero power is 1, a letter to a zero power is 1. Let's take a look at some roots. Now you're probably familiar with the square root. The square root undoes a square. The square root of x squared is equal to x. But there's other roots as well. We can have a cubed root, which undoes a cubing. So the cubed root of x times x times x, which is just x cubed, is equal to x. There's really no limit on what roots we can have, except for 0. You can have a first root. It doesn't make a whole lot of sense. You can even have fractional roots. But every root we need to think of as a fractional power. So the nth root, that is some generic root n, is actually exactly the same as a fractional power 1 over n. Let's take a look at some exponents and roots on numbers. Again, we can distribute this power to the top and bottom of the fraction separately. So in order to figure out what negative 4/5 cubed is, we can cube the top and the bottom separately, and we get negative 64 over 125. If we have a fractional power, in this case a 3/4 power, that means that we're cubing it as well as using a fourth root. And it's actually up to us which part we want to do first. We can do the power first or the root. So 16 to the 3/4 power, I can use the root first. The fourth root of 16 is 2. And then I can cube the 2 to get 8. Or if I want, I can cube 16 first, get 4096, and then take the fourth root of that. Now I tend to do the root first because it keeps the numbers from getting real big like this. Either way though, we should end up with 8. Let's take a look at a cube root of 24. Now the cube root of 24 doesn't work out nicely. But if we factor out 24, it factors all the way to 2 times 2 times 2 times 3. So we can use part of the cubed root. We can take the cubed root of that 2 times 2 times 2, or 2 cubed, and get 2. So that 2 can come out front, but the 3 can't, because there isn't a 3 cubed, it's just 3. So we'll leave it as 2 times the cubed root of 3. That's what we refer to as an exact answer. As soon as you plug this into a calculator, you're going to get an approximation. We prefer exact answers in math like precalculus. So let's just leave it like 2 to the cubed root of 3. Let's take a look at something that you're going to have to do on the homework, and that's simplifying expressions that have a lot of different powers on them. Now, 3 things that we want to do. 1, get rid of parentheses. 2, we want to combine as much as we can. We want to combine and cancel letters top and bottom of the fraction wherever we can. The third thing we want to do is we want to make sure that there's no negative exponents. So let's take a look at this top expression. And the first thing I'm going to deal with is that negative exponent. That negative 2 is telling me that that x term is in the wrong part of the fraction. So I'm going to push it down to the bottom of the fraction to join the xy squared. Now as soon as I do that, I get y on top, and all my x's combine to be x cubed and then y squared on the bottom. So now what's left to do is to cancel the y on top with one of the y's on bottom. And I'm left with 1 over x cubed y. Now if this was a homework problem, you would box that answer in. Let's move on to the second expression. We've got a lot going on here. We've got some numbers raised to some powers, and we've got letters everywhere. So, first thing I'm going to do is get rid of the parentheses. The first set of parentheses is pretty simple. Negative 2 cubed is negative 8. The second set of parentheses I'm going to get rid of by distributing that power to the y and the z. I went ahead and squared the 3 also to get 9. Now everything's got a positive power, so it's not like I have to move them around. But since I have similar terms, top and bottom, I'm going to want to factor as much as I can, cancel out top and bottom as much as I can. So x to the 4th on top, x on bottom, I can do some canceling. Y squared on top, y cubed on bottom, I can do some canceling. Z squared on top, z to the 4th on bottom, I can do some canceling. My final answer is negative 8x cubed on top, 9yz squared on bottom. Now, this last expression is a real bugger. We've got some negative exponents, so we need to deal with that. But we can't just switch them top and bottom because of the addition that's happening on top and the subtraction that's happening on bottom. So we're actually going to make this look a little bit uglier first before it gets better. So I'm going to change it. Instead of x to the negative 1, I'm going to make it a little fraction. 1 over x plus 1 over y. And I'm going to do the same thing on the bottom. Now, in order to make it nice, what I'm going to do is multiply by xy top and bottom. The reason for that is that's my common denominator, and that will get rid of all these tiny little fractions inside the big fraction. When I multiply the top by xy, and when I multiply the bottom by xy, I end up with y plus x over y minus x. So I don't have any parentheses to get rid of. I no longer have any negative powers, so I'm done with that one. Now, you all know what the Pythagorean Theorem is. Usually you write it as a squared plus b squared equals c squared. Technically what this means is that the short sides of a right triangle, you add the squares, and that's going to equal the square of the third side, the hypotenuse, the longest side in the triangle. One of our most common uses for this is to find that missing third side. Now, in a triangle where we know the two legs are 10 and 13, we can use the Pythagorean Theorem to find the hypotenuse. So we'll use c equals the square root of 10 squared plus 13 squared to figure out what the length of the hypotenuse is. And we find out that it's the square root of 269. Now, that square root doesn't get any easier, so we'll just leave it like that. There's another use for the Pythagorean Theorem, though. It checks to see if a triangle is a right triangle. If we have three sides for a triangle, 14, 24, and 26, is this a right triangle? We can use the Pythagorean Theorem to test this. If it's a right triangle, that means that it should fit in the Pythagorean Theorem, and I should get a true statement. And if it's a right triangle, the longest side is c. So I'm going to see if 26 squared equals 14 squared plus 24 squared. It's always the longest side in c, and then the shorter two sides are in a and b. It doesn't matter which one. So 26 squared is 676. Is that equal to 196 plus 576? No, it's not. We get a false statement, so that means that this is not a right triangle. So it's another good use for the Pythagorean Theorem, testing to see if a triangle is a right triangle. So, we've covered everything. You should already know what the homework is, but here it is again for the section. It's page 14, numbers 23 through 83 every fourth. Now that's a little bit odd, but if you just stop and think, 23 add 4 is 27. So after 23, you're doing 27, then 31, then 35, and so on. Another way of saying this is that it's every other odd. So it looks like a whole lot of homework, but it's actually not. So, we're all done with this lesson. It's time to get to work. I hope you enjoyed it. I'll see you in class, and I'll see you in the videos.